All right, in this big ideas, Algebra 2, Section 4.4, we're going to factor polynomials. So that's going to be one of the main learning objectives, and then also to use the factor theorem. So a couple special cases that we've talked about previously, but extending them to higher degrees. We've talked about sum of two squares. Now with the sum of two cubes, the only thing that is different is you're pulling out with that a plus b, and then your second term is having your a squared minus ab plus b squared, and then the difference of two cubes, which again is different because it's subtraction, your signs are just switching. So instead of a plus b here, becomes an a minus b, and then instead of your second term being a negative, it's now all three are being positive. So you can see over here on the right with three examples that are actually worked out. 64 is a perfect cube because you take the cube root of 64 to get 4. Same thing with 27 and 8. So these shortcuts only work if you have perfect cubes. So we're going to look at a couple of examples on how we can factor some of these completely using a bunch of different methods. So part A, we're given x to the third minus 4x squared minus 5x. We can take out the greatest common factor out of each of these, which they all have an x in common. So you take an x out of all three terms, you're left with x squared minus 4x minus 5. And then inside that parentheses, you can factor that quadratic trinomial with your AC factoring method. So finding two numbers that multiply to equal -5 but add to equal -4 is -5 and +1. And those are your two factors, and that is completely factored. Part B, you have two different terms. This is a binomial. One of them is a power to the 5, one of them is a power to the 3. So let's take out our greatest common factor. They both have a 3, and they both have a y to the third power. So that's what we're going to take out in common of both. And then notice your y squared minus 16 is a difference of two perfect squares because 16 is a perfect square. So it becomes y plus 4 and y minus 4. Part C, you have a trinomial, 5z to the fourth, 30z to the third, and 45z squared. Each of those coefficients can be divided by 5, and they all have a z squared in common, so that's your greatest common factor. And then you're left with a trinomial that, again, can be factored by taking two numbers and multiply to equal 9, but add to equal 6, and that's 3 times 3. You can write that as a z plus 3 or z plus 3 squared. All right, so factoring out using some of those shortcuts that we talked about in the first slide. X to the third minus 125 is the difference of perfect cubes. 125 is a perfect cube. So you're going to write that in terms of what you can take the cube root of 125, and that becomes 5. And then use that to then apply that pattern that we talked about in that first slide of that core concept. Then for part B, 16s to the fifth, 54s squared. So first you're going to take out your greatest common factor. They both have a 2 and an s squared. And then what you're left over with in the parentheses is the sum of perfect cubes pattern. So you're going to write that as a 2s to the third power and then a 3 to the third power. And then to use that sum of two cubes pattern that we talked about in the first slide, you take that 2s, you take that 3, you put it in front, and then you square the first term, multiply the middle term, and then square the final term. Okay, looking at something that has 4 terms is going to be done a little bit differently than what we've done in the past. So with trinomials, you've taken the final term, figured out what multiplies to equal that last term, but then adds to equal your b. But with 4 terms, you're going to need to group them into 2 different parts and then factor out something that is in common. So in the first 2 terms, between z to the third and 5z squared, they both have a z squared in common. So that's where this red z squared comes in. You're GCFing just the first 2, and then you take the last 2, you GCF the 4z and then -20. They both have a -4 in common. Notice how when you're pulling these out by grouping, what's left over in the parentheses is the same. So you then are going to use your distributive property by combining like terms. The red terms go together in front and your blue term is there at the end. Then you have your difference of perfect squares for this one, z minus 2, z plus 2. All right, so determining whether a factor is a factor of a function, and then being able to apply that using your factor theorem. So first we're going to look at plugging in our f of 2 into that function to determine if that's going to give us 0. Remember back in our remainder theorem when we were doing dividing polynomials, this is the exact same thing. So we're plugging in that value into the function. You get 4 plus 4 minus 4, and you get a value of 4. So because it is not 0, the binomial x minus 2 is not a factor of that function. Looking at part B, so we're going to find -5, and we can also use synthetic division if we don't want to plug it in. So you plug in -5 out as your k term on the outside, using your coefficients of 3, 15, -1, and 25. So bring it down, multiply, bring it down, multiply, and continue all the way down. And your last term is a 0. So since your remainder is 0, x plus 5 is a factor of that function. So if a polynomial has a factor of x minus k, that will only happen if that is equal to 0. So think about that last problem that we just went through. If you get 0 after plugging it in, then yes, it is a factor of that function.